So in this last part, we'll take a look at inverse trigonometric functions. So to fix our thoughts, let's talk about what an inverse function is. So if I'm given a function f of x, which gives me a y, then the inverse function is denoted by f minus 1 superscript, and it's such that f inverse applied to f of x is x, and f applied to f inverse, let's call this y, is equal to y. So in a sense, the inverse function undoes the function. So if we look at the graph of sine of x here, then we have a problem because of our periodicity. So if I have given here a y value, and I ask myself what x corresponds to that y value, there are many different x values that satisfy that. So I have one here, here, and then with 2 pi periodicity also here, here, and so on. And I also have that in the negative direction. So that poses a problem for our definition of the inverse sine. Because given such a y, which x value to associate with it. And once again, all of these x values map to the same y under sine, so they all a priori serve the same purpose. So the solution here is going to be to restrict the domain of sine x, and we'll restrict to the interval minus pi over 2, pi over 2. So on the figure, that means pi over 2, that's about here, and minus pi over 2 is on the other side, and the graph here looks a bit like this. Nicely to minus 1 here. And we have this part of the graph. And now if you look at this part of the graph, what you see is, given a y, there's always one unique x value that corresponds to that y if you go in this direction. In this case, it's this x value right here. So what we have is, for each y in the interval minus 1, 1, there is a unique x in minus pi over 2, pi over 2, such that sine x is equal to y. And now with that convention, we can define the inverse sine, which is sometimes also denoted as the arc sine or the A sine. We can define this as sine inverse of y is equal to that value x. So sine takes x and turns it into y, sine inverse takes y and gives you back x. And this is defined for all y between minus 1 and plus 1. And if you look at this a little bit closer, you can see right away that there's some nice cancellation properties. If we apply the inverse sine to the sine, we get back our original x, but that's only true if x is in the interval minus pi over 2, pi over 2. And likewise, if we apply the sine to the inverse sine of some value, we get back our value that we started from if y is in the interval -1, 1. So that gives us our inverse sine. Now we can do the same thing for tan. So here, remember, we have pi periodicity. So what we will do here is restrict the domain of tan to the interval minus pi over 2, pi over 2, the bounds not included. So that means that we look at this part of the graph only. And if this is our y-axis, then again you can check the same property as we had for sine. So given a y between negative infinity and positive infinity, given a y, we can always find a unique x in the interval minus pi over 2, pi over 2, such that tan of x is equal to y. And for that value of x, we say, so definition, the inverse tan of y is equal to that x value. So the interpretation is the same as for sine. You're given the y value and you find the x value that corresponds to it. So you go in the opposite direction. And now the properties are also very similar. If I apply the tan inverse to the tan of x, I get x back. If x in the interval minus pi over 2, pi over 2, and if I apply the tan to the inverse tan of y, I get y. And here there's essentially no restrictions. There's an empty one. Y has to be between minus infinity and plus infinity. So now the next one up is the inverse cosine. So cosine inverse of y. And again, we're going to do the same thing. But here we will restrict the domain of cosine to the interval 0, pi. And I don't have a graph here, but that's basically for the same reason as before. So the graph of cosine looks like this. So it decreases until it's pi over 2, where it becomes 0. And then for pi, the graph is, or the value is equal to minus 1. So here we have plus 1, and here we have minus 1. And so we restrict to this interval precisely because now we can play the same game. Given a y, there's always one unique x associated to that y. And so what we get from that is that with the notation from the figure, cosine inverse of y is x, and that x is in the interval 0, has to be in this interval and be such that cosine x is y. And here the cancellation properties are that cosine inverse cosine x is x, again for x in 0, pi, and cosine inverse y is equal to y, and here y has to be between -1 and +1. So this is actually one definition. This is what I would call the direct definition. There's also another definition via the inverse sine. Let's have a look at how that goes. So let's start with the relation x is equal to cosine inverse of y. Then we know that y is cosine of x. Cosine x is sine pi over 2 minus x. And now what we have is that if we apply sine inverse to both sides, sine inverse of y is sine inverse sine pi over 2 minus x. And this is pi over 2 minus x. And since x is cosine inverse, this is pi over 2 minus cosine inverse minus y. And if we clean this up a bit and we look at what we have on the left and on the right, we get that cosine inverse of y is equal to pi over 2 minus sine inverse of y. This is also a useful relation to keep in mind, and it basically says that there's these two functions differ by pi over 2. There's a few more properties that you can derive in a similar vein. So the same thing holds true for the inverse cosecant, the inverse secant, and so on. But I'll let you play with that a little bit. And before we move on, actually there's one more that I have to show. So you can also define the inverse cotangent, as we already did. And if you follow the same reasoning, you'll find that the inverse cotangent is equal to the inverse tangent of 1 over y. So this is quite a nasty-ish function. It's a bit unknown, but it tells you this identity that you can turn it into inverse tangent. So the caveat that I have on the slide here is a very important one, because there's always some mistakes against that and it's totally invalid. So you have to keep in mind that sine inverse of y, so this is the inverse sine function, this is not at all equal, this is very different from 1 over the sine of y. So every year there's people that confuse the two on the exam, and it completely ruins the solution. So to wrap up, let's do a couple of examples. So for the first example, we'll compute the inverse cotangent of negative square root of 3. And for that we can use the property that I just highlighted. This is the inverse of -1 over square root of 3. So this is less than 0, so we have to find an angle whose tangent is equal to -1 over square root of 3, and that's going to give us minus pi over 6. Second example, just to get some practice, if we take the tangent of the inverse tangent of 10, here we can use one of the cancellation properties. If you apply the tan after you apply the inverse tan, you get back the original value. You always have to be a bit careful about what condition, because we have to restrict, but here there's no condition that applies, because the tan inverse is defined for all possible values of y. And then a couple more involved examples. So for the third example, we'll look at tan of sine inverse of 2 over 3. And it always gets interesting when there's different trigonometric functions involved, but there's a procedure to solve them. So as a first step, what we'll do is we'll call this here equal to theta. So then what we have here, and I'll put it separately, is that theta is equal to sine inverse of 2/3. And so in other words, sine theta is equal to 2 divided by 3. So in order to understand a bit what the angle theta is, let's draw a right angle triangle. And let's call this angle right here theta. And then the sine is the opposite divided by the hypotenuse. So that's satisfied if the opposite is 2, for instance, and the hypotenuse is 3. It doesn't have to be those values. You can also multiply them by a constant, but those are arguably the simplest values that give you this sine. And with these two values, then the adjacent is equal to square root of 5. You can calculate that with Pythagoras' theorem. And this is interesting because this also tells us that tan theta is equal to the opposite divided by the adjacent 2 over square root of 5. So given that we had to calculate the tan of theta here, this basically gives us our answer, 2 over square root of 5. But there's one thing that we have to check, and that is the signs. So if you do this reasoning with the right angle triangle, you have to be very careful, because in a triangle you only have positive sides. So you basically lose a bit of information if you make this reasoning about the signs. So let's go through that calculation carefully. So theta is equal to sine inverse of 2 divided by 3. So this is a positive value, and that tells us that theta is in the interval 0 to pi over 2. From that, we know that the tan of theta is going to be in the interval 0 to basically plus infinity. So in particular, tan theta is positive. And that tells us that yes, our answer is correct. It's the plus 2 over square root of 5. And in a second, we'll see an example where the signs flip, where you get the right magnitude, but you have to adjust the signs. Okay, so for the last few examples, we'll do a couple that have a slight twist. So the first one is sine inverse sine of 7 pi divided by 3. So here you might be tempted to use the cancellation rule, but that would not be immediately correct. So this angle is not in the interval minus pi over 2, pi over 2. So we cannot use the cancellation rule right away. But what we can do is we can write this as sine of 2 pi plus pi over 3, and then use the fact that sine is 2 pi periodic to write this as sine of pi over 3. And now this angle is in the interval minus pi over 2, pi over 2. So we can use the cancellation property to write this as pi over 3. So you see, sine inverse after sine doesn't always give you the same result. 7 pi over 3 here and it's pi over. For the last example, we'll have a look at cosine of tan inverse 2 plus tan inverse 3. We use the same principle. We call this alpha and we call this beta. So we have that alpha is tan inverse 2, beta is tan inverse 3. And in particular we have tan alpha is 2, tan beta is equal to 3. So what else do we know here? Well, from this we can also derive that alpha is in the interval 0 to pi over 2, and beta is in the same interval 0 to pi over 2. And that follows from the fact that these angles have positive tan values, tan 2 and tan 3. And since we have to say something about cosine alpha plus beta, we can also take a look at alpha plus beta, and we know that alpha plus beta is going to be in the interval 0 to pi with bounds not included. So in other words, alpha plus beta is in quadrant 1 or 2. And now, moreover, we can look at the tan of alpha plus beta. We have that that's tan alpha plus tan beta divided by 1 minus tan alpha tan beta. And if we substitute the values that we have, 2 and 3, we get 2 plus 3 divided by 1 minus 2 times 3. And that gives us minus 1. So we have that the tangent of alpha plus beta is negative. So what do we know? Well, alpha plus beta is in quadrant 1 or 2. We know that tan alpha plus beta is negative. And from that it follows that alpha plus beta has to be in quadrant 2. So this is going to be an important relation because it also tells us that cosine alpha plus beta itself is negative. So now we know the sign of cosine alpha plus beta, we also need to calculate the value. So for that, let's take a triangle. We put alpha plus beta here. And we know that the tan of alpha plus beta is equal to minus 1. But in a triangle, you can't have negative sides, so we have to work with the absolute value, 1. So a triangle where the tangent of alpha plus beta is 1 is given by the following one, where the adjacent and the opposite are both equal to 1. And then the third side, the hypotenuse, is equal to square root of 2. So in this triangle we have that tan alpha plus beta is 1. So note the sign here. We also know that cosine alpha plus beta is adjacent divided by hypotenuse. That's 1 over square root of 2. And now we can go back to our expression. We had to calculate cosine of alpha plus beta. We found from our triangle that that's 1 over square root of 2. But because of this sign calculation that we did here, we see that we actually have to change the sign and put a minus here to have an answer that is negative. So minus 1 over square root.